Assalamualaikum warahmatullahi wabarakatuh. Selamat siang Bapak-Bapak, Ibu-Ibu semuanya di seluruh Indonesia yang bergabung di acara webinar kami PT Testindo yang ke-8 hari ini. Siang ini ya, tadi pagi kita ada webinar tentang monitoring kesehatan struktur dengan loading test. Nah, siang ini kita akan membahas tentang NDT untuk beton. Kira-kira begitu. Mr. Andre telah menyempatkan hadirkan waktunya untuk kita sharing ke kita tentang teknologi state of the art and novel trend in instrumentation for ultrasonic concrete. Intinya adalah bagaimana perkembangan evaluasi kondisi beton, baik itu secara kita inspeksi manual di lapangan gitu ya, maupun ada online juga untuk mengevaluasi kondisi beton. Nah, jadi hari ini kita akan diskusi tentang itu siang ini dan Mr. Andre akan presentasi 60 menit. Setelah itu pertanyaan silahkan disampaikan, bisa chat ya. Nanti kita akan balas satu persatu. Beberapa akan dibalas, akan diusahakan semua dijawab lah sama Mr. Andre. Oke, Andre, please start your presentation.
One second, I hope I will manage. Oh, this is the wrong one, probably. Second. This one. So, can you see my screen?
Yes, I can see.
Okay,
Yes,
good. So I will proceed. So, good afternoon together. Good morning for me in Germany. Yes, the topic of my presentation today is state of the art and novel trends in instrumentation for concrete testing by means of ultrasonic. And to give you a short overview, what will be the, let's say, the content of the presentation. I'll start a little bit with a basic principle of ultrasonic testing, how it is applied in regular, let's say, field of metal a little bit, and then we will come slowly to the needs and demands of the NDT in civil in industry, civil engineering, and possible application fields will be presented. And then I come to the main topic, available instrumentation. So, and then you will see that actually we can subdivide the application in two main fields. It is material evaluation, where we try to estimate the mechanical properties of concrete, and the second part is ultrasonic imaging and material flow detection. And then finally, I will present the newest trends in the equipment and in the techniques, which are mainly concerned about the imaging. So, as I have told, the ultrasonic testing is a very wild used technique. And in general, if I have tried to, let's say, exemplify the idea of UT with this page, the main, let's say, technique which is used for UT is so-called pulse echo, where from one side, from one insonification surface, we apply a transducer, and we get echo signals. And if, let's say, very simplified, we have no defects inside of the material. We only can see, let's say, the reflection from the back wall echo. And if there is a defect inside, we'll see some flow defect echo, and the estimation of the size is according to the state of the art based on the amplitude information. That means the big defect big signal or strong signal, small defects, smaller signal, and the estimation is based on the sensitivity calibration. Means before we go for the testing, we calibrate the instrument on some reference specimens with the artificial defects, yes, and then we compare the reflectivity of the real defect with the reflectivity of the artificial defect, and give the values of the, let's say, the defect size and those artificial defect units. Might be flat bottom holes or side drill holes or notches or whatever. So, and obviously this approach is not perfect because the reflectivity of the defect may depend not only on the let's say the size of the defect, but also on the type of the defect. Like volumetric defects, they reflect in all the directions, while flat defects like cracks, they have some destinated beam directivity, so that not every transducer is capable to catch it up. And a little bit for that reason, the so-called phased array technology has been developed and applied, let's say in the early 90s of 20th centuries. And actually the basic application of this technology was not NDT, but medicine. Everybody knows that. Finally, it came also to the NDT, and the idea of the technology is to change the angle of incidence by electronic steering of the sound beam. So this is visualized in this slide. In the medicine, the amplitude information is represented by grayscale colors, and in the NDT it is typical real colors. And this is how the inspection result looks like. Then there was another, let's say, a very popular technique before phased array, so-called synthetic aperture focusing technique, where even before people have started to use phased array, so that means multi-element transducers, a very powerful imaging technology was applied, where the inspection object has been scanned by a two-axis manipulator, and finally by a specific reconstruction technique, SAFT or synthetic aperture focusing technique, a very accurate representation of the defects was provided. So, and it was available even before a phased array. So why I am talking about that, the current state of the art is actually a combination of those two techniques, phased array and synthetic aperture focusing technique. The idea is, while yes, we are using multi-channel, multi-element transducers, but we were able to reconstruct or to process the data according to the synthetic aperture focusing technique. And this is a very, very accurate technology, or let's say very powerful, very advanced technology, while we are firing elements not together as it is done in a regular phased array technique, but firing them separately. We can collect the data from all the directions simultaneously. And that means even after one single shot and collecting the data with all the elements of the phased array transducer, we can obtain so-called information matrix with the individual wavelets individual A scans for each combination of pulse and receiver, and then apply this SAFT, or nowadays it is called total focusing method, to obtain a very, let's say, well resolved with a high resolution image. So, and the near field of the phased array transducer. So you see the how it looks like, and now we are coming slowly to the, let's say, to the needs of civil construction industry. Yes, there are plenty of inspection tasks. First of all, I must say the need on the NDT is quite huge, because the infrastructure is not getting younger, it is getting older worldwide. That means the need on the quality assessment of the civil infrastructure will only grow, and the novel trends nowadays, it is going, let's say, step by step towards the same as has been done in a regular, let's say, metal or steel industry a long time back. So that step by step personal qualification is introduced, equipment qualification and certification is introduced for instrumentation for construction industry, and application codes and standards will appear very soon. The pioneer in this field is obviously China, since they have in the last 10 years, let's say, created the same amount of concrete infrastructure as the rest of the world. And also, I'm quite honest, let's say our main field I mean, our main sales are mostly happening in China currently. So, but also in some European countries, like in Italy and in Germany, the trend in the development of the NDT for construction industry goes the same direction. Means personal qualification, instrument certification codes and standards, and then application codes and standards. So, but what are the tasks of the NDT? We're talking about need of data collection about the inner structure of the object, and in many cases it is in not even, let's say, flow detection, yes, but we just measure let's say the wall thickness, or approve the presence of reinforcement, for example, yes, since due to the lack of information. So obviously we would like to have some estimation of the current state of the structure, and compare if it is corresponding to the documentation. Would like to estimate, to find defects, yes, to estimate the level of damage, and probably take a decision on need of repairs, or maybe yes, even more complete destroying of the building because it is out of range already. So but at the same time, from the very beginning, I have to say about, let's say, the limitations of challenges of the ultrasonic testing on concrete structures. They are of two types. First of all, these are physical limitations, which one has to keep in mind. And second, it is, let's say, methodical or organizational limitations. First of all, opposite to metal, concrete is a very heterogeneous material. And if you talk about the ultrasonic, it will quite strong structural noise will be there, because of this heterogeneity. So while in the metal testing we are using rather high frequencies of ultrasonic waves, like let's say the mainstream it is between 1 and 10 megahertz. So that means the wavelength of the UT applied is about, let's say, 1 millimeter. And this is our sensitivity and resolution approximately. In For testing of concrete, we have to use low frequencies, let's say between 10 and 100 kilohertz. That means the regular wavelength which we apply is about, let's say, 50, 60 millimeters. And this is approximately our sensitivity and resolution. So that means we cannot expect we can find find and visualize micro cracks. Vice versa. I will give it in the next slides. Let's say the regular reflector, let's call it this way, we can visualize by using ultrasonic imaging is, let's say, about 15, 20 millimeter in diameter. We are talking about the rebars, or let's say 20 millimeters in diameter. We are talking about, let's say, volumetric reflectors like some cavities. So second, concrete is normally not just a concrete, it is a structurally complex material containing other, let's say, elements made of steel or plastic or whatever, for example, reinforcement and so on. And obviously, if we have too much metal inside, we cannot talk anymore about the concrete testing, as it is really it becomes more challenging, and there are cases where we have so many metallic elements that the inspection is even not possible. So, and large dimensions, of course, it is also another challenge, and limited accessibility. I mean, if it is some skyscraper and you have to inspect from outside, it is also obviously a challenge. Coming to the, let's say, organizational limitations, this probably the main, let's say, the main obstacle is if people buy our equipment, in very many cases they come back to us because they need the guidance how to apply it. And while for let's say regular metal world, where we're, I mean, like oil and gas industry, yes, or steel production industry or aircraft industry or whatever, the application of UT has a very, very long history of, let's say, 50, 60 years. There are codes and standards available for application of UT. I mean, every level 2 guy knows which code he has to take to write a written procedure how to perform, for example, of weld inspection for a pipe with a certain wall thickness and certain weld preparation. Yes, it is like worldwide available, and there are no let's say limitation how to proceed. In for the concrete testing, it is just vice versa. In most of the cases, there is no methodical guidance at all, and these codes are just in preparation. I mean, maybe it will take another few years till it is really available for the wild practice. And for that reason, the inspection results are very much dependent on the operator professional skills and experience. And every inspection object in this case might be considered as a, let's say, a very specific or original. Yes, obviously there are general, let's say, tasking like, I mean, if we want to measure the wall thickness, then it is just a wall thickness. So if we want to find the rebars, then these are just the rebars. But the challenge is, yes, the application rules depend very much on the physical properties of the material, and let's say the application. I mean, if you are not very experienced guy, not very experienced operator, you will have very many questions how to proceed. Yes, and that's why most of our customers are also after the buying the instrument, they are coming back to us and asking how we should go ahead. So nevertheless, despite of all these limitations, UT is I would say a part of the ground penetrating radar. This is the main, let's say, NDT method applicable and suitable for concrete testing. The main, let's say, advantage of UT is a high penetration depth, while having a relatively high sensitivity and resolution. I mean, obviously there are two main techniques for volume inspection, volume visualization. This is a GPR, ground penetrating radar, and UT. GPR is a very fast technique and also quite powerful, but the detection capability of GPR is in general a little bit lower, especially if we are talking about reinforced structures where the metal, especially if these are several layers of reinforcement, is just shielding the penetration of electromagnetic waves, while UT is capable to penetrate deep at relatively high frequencies. So, and providing 2- and 3-dimensional imaging of the structure. So we can apply different techniques for let's say signal processing and image visualization, image reconstruction. There are different techniques like pulse velocity testing or tomography, which I will exemplify a little bit later. And another, let's say, capability of UT, the transducers we're applying, they are rather broadband transducers so that we can adjust our working frequency according to the need on site. Means we can go over the low frequencies or over the higher frequencies depending on what material allows us. Nevertheless, those physical limitations which I have already mentioned, like high structural noise and strong frequency dependence of sound attenuation, and structural complexity. If we have too many, let's say, rebars inside, it makes, of course, the application yes, quite challenging. So that the operator must understand very well the application rules. Yes. And again, I point out what are, let's say the sensitivity and resolution. No microcracks can be found in the concrete by UT because of the rather, let's say, big wavelength values. So now coming to the available instrumentation for UT, it can be, I mean, they can be subdivided in, the instruments can be subdivided in two main or two major groups. First of all, these are instruments for material evaluation. And that means we estimate the mechanical properties of concrete. And second, instruments for ultrasonic imaging and flow detection, where we find and estimate the size of the defects inside of the material. If I look a little bit back, yes, the ultrasonic instruments, for example, for weld testing in the oil and gas, they have much longer history. Yes, already in the early 60s, there were yes, flow detectors or thickness gauges at least available. While for concrete, the first instruments, they have appeared just some maybe 30 years back. So the history is much shorter. Nevertheless, there were very different instruments for imaging. Initially, they were based on a regular piezoelectric technology. Later, so-called dry point contact transducers came into the picture, and yes, already in early 2000, there were phased array instruments for yes, for imaging on site. Finally, it came to the 2 and 3 dimensional imaging of the structure, and I would say step by step, at least from the technical point of view, also ultrasonic instrumentation for concrete is reaching the state of the art of, let's say, regular phased array instrumentation for metal testing. So the main, the key element, let's say, of the ultrasonic instrumentation are so-called dry point contact transducers. If we talk a little bit about the physics, there are, let's say, 3-4 different methods to generate ultrasound in the material. The main is, of course, regular piezoelectric transducers, where the crystal is just vibrating, and by applying the high voltage and generate the sound inside of the material. But obviously, we need some couplant to provide the penetration of the sound into the, I mean, from the crystal to the material. And this is also a challenge in many cases, because there are rough surfaces or corroded surfaces or dirty or painted or coated surfaces, so that it doesn't work always well, and it might be also quite, let's say, a limitation for the concrete testing, for example, because application of couplant liquid on a big large, let's say, surfaces is quite yeah, time consuming and expensive. Another technique available is so-called electromagnetic acoustic sound generation, where conductive materials are capable to receive ultrasound by just electromagnetic principle, or Lorentz forces are used, but unfortunately it's not applicable for concrete because it is not conductive. Then there is a so-called laser ultrasound, where the surface of the object is heated up uh, by the laser, and the receiving is happening by using interferometer instruments. But all this is too specific and not really applicable for concrete testing. So the best solution for concrete are so-called dry point contact transducers. In general, they are also somehow piezoelectric, because each such individual element contains piezoelectric crystals inside, made of on a special way. But finally, the vibration is transferred to the material by means of the pin. And this principle was intended and introduced by our company, by Acoustic Control Systems, long back, like over 30 years back. And now very different transducers with the different frequencies, with a different, let's say, type of generated waves are available, like shear waves and longitudinal waves and surface waves can be generated. In most of the cases, we don't use transducers individually because in order to penetrate deeper, we need more energy as one transducer can provide, so that we apply them, those transducers, as transducers arrays. And this is a direct way to the phased array technology because yeah, many elements allows us to apply the total focusing method and full matrix capture technology to process the data. And another thing which is important, I mean, as I have mentioned, longitudinal waves and shear waves can be generated by it, but for ultrasonic imaging purposes and for flow detection, the shear wave is, let's say, the more applicable and the more advantageable wave art. So that while for ultrasonic pulse velocity testing, longitudinal wave is applied more frequently, or let's say actually the only wave art which is used and common for imaging purposes, shear wave transducers are used, or shear wave transducer arrays. Yes. Okay, this I think I can skip, but you see, for example, simultaneously by the same transducer, which can be considered as a point source from the physical point of view, we can generate shear wave in the volume and longitudinal wave on the surface, and vice versa, which is, for example, used in one of our instruments, which I will exemplify later. So yes, those arrays are of very different art. I mean, sometimes we use transducers which are damped to have higher spatial resolution, energy to penetrate deeper. And coming to the let's say instruments which are available, as I have already mentioned, the first category, these are so-called ultrasonic pulse velocity testers, abbreviated by UPVT. The second category, which can be actually combined with the third category, these are already instruments for thickness measurement and sometimes for flow detection, but using a single channel data acquisition electronics. And it can be extended to the multi-channel systems or tomography systems, which apply total focusing method. And the most common name worldwide is MIRA. This is our yes unit, which is already nearly since 15-16 years on the market. So it is just yeah, the main name for ultrasonic tomography, more or less, on the concrete structures. So and these are the equipments. On the upper side, you see these are two pulse velocity testers. These are rather low-cost instruments, easy to use instruments, and on the lower side of the screen you see flow detectors and tomography systems which are more advanced and more expensive instruments. So, and I will show it now in more details. So the general principle of ultrasonic pulse velocity testing is dependency of compressive strength of concrete or some other materials uh, from the ultrasonic sound velocity, or rather, not the dependency, but let's say the connection of these two parameters. That means if we measure the sound velocity, it is correlating or corresponding to the compressive strength of the material. So means by appropriate calibration on reference blocks and getting the calibration curve, we can, by means of ultrasound, directly measure the compressive strength in megapascal on site. And this is a very, very common technique, very wide applied. Yes, there are different, let's say, insonification schemes which I used. For example, we can measure indirect through transmission, indirect through transmission over the corner, and then the indirect method, or it is also called surface through transmission. So the principle is simple. We just fix the distance, so-called base, between two transducers. We measure the time, and by dividing distance by the time, we obtain the sound velocity value. And this sound velocity value is somehow corresponding to the compressive strength of the material. So this is how it is implemented in our A1410. Yes, just choose the transmission type, direct or indirect, and then the instrument. We choose the base value. For example, in this case, it's 150 millimeters. This is the distance between the transmitter and receiver, and we obtain the sound velocity value in meters per second. Or if the instrument is calibrated, we obtain the value in megapascal directly, the compressive strength value. So here I will show a short movie. Oops. No, shit. I have removed the movie. It's okay. So then there is a simplified version of the same, where even the operator doesn't need to choose the base because it is fixed. This is a very simple to use instrument, so-called surface pulse velocity tester. Yes, and here, as I have already mentioned, for example, we're using dry point contact transducers, which are generating longitudinal wave on the surface of the object. Yes, directly. So the let's say the limitation or disadvantage of this instrument, it is measuring only on the surface. Yes, while the A1410, the previous instrument, is more universal. You can implement different insonification techniques. Yes, this is the idea. Again, by a fixed base, it is very easy to measure the sound velocity value. So the next category, single channel instruments. You see, there is a very basic pulse echo principle, which I have exemplified previously. We obtain echo signals and The strongest signals we can ever obtain from the material is the backwall signal. That means the backside of the component. So that means if we are capable to catch up the backwall signal and we know the sound velocity value, we can um, measure the thickness, yes, and vice versa. If the backwall signal is disappearing sometimes, that means something might be inside, yes. Uh, this is so-called shadow method, yes, where by collecting the data over the surface and we are just looking to the positions where the backwall has disappeared, which might be the indication for some defect. Or we directly, if there is some delamination inside, our backwall signal will be just on the wrong position, not in the full depth, but somewhere in between. So the instrument which can be let's say put in this category is our A1220 monolith, also quite let's say popular instrument for relatively simple to use, but we can go to the next stage with the same. If we mark our surface and collect the data in equidistant depth, equidistant steps in an x and y direction, we call it index and scan direction, we can apply the same synthetic aperture focusing technique and obtain a three-dimensional data, so that we call our A1220 monolith instrument a monolith 3D, because by means of the 3D reconstruction software, which is a part of delivery volume, we can really obtain accurate three-dimensional images of the inspected object. The next stage of the ultrasonic equipment available is a multi-channel tomographic systems. Like I have already mentioned, the Mira A1040, which is a real-time TFM imaging system applying total focusing method, and it is capable of visualization of reinforcement components and flows with a very long, let's say, inspection range up to 1 or even 2.5 meters in concrete. So yes, the principle is similar to yes, what you probably will know from the doctor. Yes, we apply the instrument directly on the surface and see the cross-sectional image, where we can recognize, for example, the B-scan indication or some rebars or material flows. And as I have already mentioned, let's say the detection and resolution capabilities in the regular case, if it is not some very, very coarse grain concrete, for the cylindrical reflector like a metallic rebar, it would be something about, let's say, 12 millimeters. Obviously, we had already cases where in a near field, I mean, close to the surface, we could detect smaller rebars like 10 millimeters only, 8 millimeters, but it is already hard on limit. And I mean, I would not promise it in every case. Then, if we are talking about spherical reflectors like some inclusion or cavities, so these are the size of those defects might be up to, let's say, 15 or 20 millimeters, something like that. So, but again, the very frequent question we get from unexperienced users are, what is the smallest defect I can find? Of course, I indicate some values now on the slide, but it always depends on the material very, very much. Because if we have a coarse grain material where we cannot apply, let's say, the instrument at higher frequencies, we have to reduce the inspection frequency to be able to penetrate at all. Of course, in this case, our detection and resolution capabilities are getting down, so that and vice versa. I mean, if it is a very, very fine concrete, we can increase the frequency and improve our uh, defect detectability. So that means we're always as good as material allows us to be. Yes, this is just yeah, a nice image provided by one of our Chinese partners. You see somehow, yes, how the imaging works, what we can visualize. So obviously these are not some micro defects. Yeah, these are uh, rather big structural, let's say, features in the concrete. The smallest, maybe some rebar, yes, like this one on side, but not very small elements inside. So as I have already mentioned, a very essential part of all those instruments for ultrasonic imaging is a external software, because the visualization capability of any instrument is rather, I mean, portable instrument is rather limited because of a smaller screen or limited um, graphic memory and so on. Finally, if we want to cover and visualize larger areas, and we have to work with the big data, which can be only processed and visualized on a PC, external PC, and essential part of which is in the delivery set of our instruments is always 3D visualization software IntraView, which is an important tool for data processing and reporting. So the next instrument, which is also available, is a small brother of the big mirror. Yes, we put it as an affordable, let's say, low-cost instrument for tomography, 8 and 20 meter light. It has a rather smaller aperture, but it is in many cases sufficient for inspection purposes, and it is also capable of 3D imaging. Yes, you see, for example, on this image, very well, we can visualize several layers of rebars, even with this small tomography system. So this is just for your information. It is rather for research and development purposes. This is an instrument, OEM instrument, yes, which can be connected to the PC, and mostly our R&D partners like institutes and universities like this instrument very much, because they can develop their own routines and signal and image processing algorithms for for data reconstruction and visualization. So what are the main application fields of these instruments? First of all, of course, this is a very basic of UT. We can measure the thickness and visualize, for example, the thickness profile. Oops, the thickness profile on the component, along with the rebars, which are probably available inside. Yes. Um, as I have already mentioned, with the UT, with ultrasonic testing, we can penetrate deep and visualize up to 3-4 layers of rebars inside of the material, which GPR is, for example, not capable of. Yes, crack sizing This is a rather novel feature, but it is already available in our new instrument A1040 Mira 3D. But also other defects like cavities, inclusions, honeycombs, cracks, and so on can be detected, visualized, and evaluated by means of ultrasonic testing. Another very important application, we have several really big customers, manufacturer of carbon electrodes. This is also, let's say, a structurally complex material, heterogeneous material, where low frequency ultrasonic testing is yes, very important part of the quality assurance while production. Yes, fireproof stones. These are also important components in the steel production. These are just few application fields where I try to exemplify where the UT by means of ultrasonic tomography can be applied. Yes, another application field important or let's say popular in Germany. It is inspection of really extremely thick-walled components. For example, for testing of nuclear waste storages. Um, yes, where we can penetrate up to 10 meters in the concrete. So, and now let's talk a bit about what are the novel trends in the UT. By its nature, the dry point contact transducers are possessing matrix aperture, and in the previous generation of ultrasonic instruments, those matrix apertures have never been used as a matrix apertures. Actually, we always connected several elements together and used this aperture as a linear transducer array. While I mean, if we really individually apply the data acquisition electronics to each element, we will be able to use or to perform real or true three-dimensional tomographic imaging. Then it will also, in the scope of this implementation, we can improve crack sizing functionality, for example, for open cracks, which I will exemplify now. Then another, let's say, very major trend is connected to the, let's say, to the modern technology, Internet of Things. Yes, that the data processing is performed no longer inside of the instrument, or let's say FPGA in the instrument or digital processor, but it is ported to the tablet PC. Yes, which is directly connected to the internet and to some cloud storages and processing systems. So and as I have already mentioned before, to really cover bigger, let's say, areas of the inspection object, we have to work with the big data, and for that we also need advanced computing and processing techniques. And these are basically four main trends in the let's say instrumentation for ultrasonic concrete testing. And here I would demonstrate a short video. So I'm not sure if you're also listening the music or not. Just now I was thinking maybe the sound was not available with you. But anyway, yes, this is our new hardware platform, which we have called A1040 Mira 3D. It is processing, let's say, several breaking through technologies at the same time. First of all, we have integrated active dry point contact transducers having individual pulsar and receiver on each transducer element, which improves the signal to noise ratio and sensitivity of the inspection tremendously. And at the same time, we were able to really perform a true 3D data collection and tomographic reconstruction at each position of the instrument, including this mentioned open crack sizing function. So it is modularly designed. We can apply 1, 2, 4, or even more elements in one aperture. And yes, visualize 3D data on the instrument itself if the data is not too large, or externally by using IntraView Pro, the new software available, where we can operate the instrument not only by using the tablet PC, but also we can control it from the regular PC by Wi-Fi. So it is a very promising, let's say, direction for us, because we're getting more and more inquiries about automation of the inspection process. Means the instrument is installed on some scanner or gondole, which is say collecting the data more or less remotely, and the operator is visualizing it and controlling the process sitting somewhere outside. So this will be available with the new instrument. Yes, short summary. Yes, modern instruments for concrete testing obviously go towards 3D imaging and visualization. And by advanced signal processing and image reconstruction, we can significantly improve the informational content of the UT. And we strongly believe that UT for concrete infrastructure reveals a very promising emerging NDT market for many participants in the future. Thank you very much. I was almost in time, 60 minutes. I hope, there will be some questions to me. Thank you for your attention.
Thank you, Andre. Terima kasih, Andre, for your presentation. Saya ulas sedikit yang dipresentasikan oleh Andre, perkembangan NDT untuk ultrasonic adalah sekarang ini selain bisa untuk asesmen struktur, dalam artian selama ini kita tahu di dalam ini ada crack atau void. Nah, sekarang ini kita bisa lihat secara lebih detail ukurannya, posisi letaknya, dan juga tadi saya lihat udah ada bisa mengestimasi ukuran tulangan di dalam beton. Jadi sekalian retak-retak semuanya telah tervisualisasi dengan 3 dimensi. Yang pasti seperti UPV ya, seperti kita udah ketahui, udah bisa mengestimasi mutu beton dan kedalaman retak ke permukaan gitu. Andre, I would like to confirm you whether in A1040 Mira 3D already capable to also predict the size of the rebar inside the concrete.
No, not really. I mean, the limitation is the same as with the old Mira. Look, in general, this possible anyway, but it is very how to say difficult to implement on the practice. I mean, obviously the different rebars will have different um, signal strengths, will provide different signal strengths, different indications. Like small rebar will give you a weak signal, big rebar will give you a strong signal. And if we would prepare a reference block containing rebars of different size, we could um, calibrate the system so that for each indication we could, let's say, okay, this corresponding uh, to this dimension of the rebar, this correspond to this dimension of the rebar. But the problem is uh, the indication intensity is not only depending on the size of the rebar. Means for each type of concrete, we would have to create such a calibration blocks, like for coarse grain concrete, for fine grain concrete, and so on, or something in between. And the problem is each user would have to have such calibration blocks. It is nearly the same with the metal testing. You know, if you go for metal testing, like for weld inspection, yes, we first calibrate your instrument on the reference blocks. The problem is metal is rather homogeneous material. Yes, it is not that strongly dependent on the material properties. Of course, there are also ferritic steels and austenitic steels, but in general, if we are talking about the ferritic steels, which are the most common, you can even use the same calibration block to calibrate any instrument for any use. Unfortunately, with the concrete, it is not the same. That means you would have to have different concrete blocks with different rebars. I mean, different concrete types. Yes, with a different size of rebars and different depth. And then, after having this calibration and these calibration blocks, you could really measure the rebar diameter. Yes, by just estimating the amplitude of the indication. But unfortunately, this very yeah expensive way. So and another approach which I have mentioned, I mean, if we visualize the indication and then just measure the size of the indication, this will not work, unfortunately, because of the big wavelength of ultrasound. We cannot resolve 10 millimeter rebar, 20 millimeter rebar, and let's say 30 millimeter rebar or 40 millimeter rebar, because our wavelength is just 50. You know, that means we cannot distinguish between those. So that means the only way would be really amplitude calibration with the reference blocks. But all this must be described methodically, you know, in the codes and standards. It will be done someday, but for now there is no proper solution, and that's why, yeah, the limitation is still there.
Okay. So I see that a lot of question from UGM, Mr. Henricus Priyo Sulistyo. Does your instrument measure automatically the distance between two sensors? It means transceiver and receiver, as well as the travel time, so that the speed will be also informed right away.
Can you repeat? I have not
That,
got the point.
does your instrument measure automatically the distance between the transceiver and receiver as the travel time, so that the speed will be also informed right away?
You mean if we have a transmitter and receiver, and
Yeah, it means if you use a like a UPV, there is a transceiver and receiver, so the distance also will be measured automatically as the travel time.
Okay. You mean if it is we measure the time as usually? I mean as any UPVT instrument, but if we have, for example, some GPR or some electromagnetic or whatever distance measurement between these transducers, and then we get the distance from this source. So this is the idea.
So the distance is calculated automatically, or we input the number?
No, look. Okay, let me try to explain it to you. We have, let's say, 3 parameters which are depending on each other. We have the distance, we have the sound velocity, and we have the time. And if you know the distance and the time, you can calculate the sound velocity. If you know the time and the sound velocity, you can calculate the distance. If you know sound velocity and distance, you can calculate the time. They are just they are belonging together. They depending from each other. So, but you cannot. I mean, that means if you know the distance, and then you measure the time. This is the main principle of the ultrasonic pulse velocity testing. You always divide the distance which you measured by the scale by the time which you measured by the instrument, and then you can obtain the sound velocity value. That's why what is the main, let's say, principle how you measure with the UPVT? You measure with the scale the distance, you enter the value into the instrument as a base, then instrument measures the time and this automatically shows you the sound velocity value. And then if it is a low sound velocity value, you say, okay, this is a bad concrete. If it is a high sound velocity value, you say, okay, it is a good concrete. But and what is the principle of the thickness measurement? This is just vice versa. You measure the time, you know the sound velocity value, and then you can show the thickness in the millimeters. But you cannot without I mean, if you don't know the thickness and you don't know the sound velocity, you can only measure the time.
Okay.
Because this, I mean, you need at least 2 to obtain the third.
Okay. Can we go to the next question, Andre?
Sure.
For how many days the concrete age, so we can test it with our ultrasonic? The question from Mr. Hadi Salam.
You mean if it is a new, fresh concrete?
Yes, yes.
In general, the point is following. If it is just a new construction, it is still a little bit, I mean, it has humidity, yes? Then it is drying slowly. The more humidity we have, the better. That means in the new stage, it is always easy to inspect. But afterwards, the sound velocity is a little bit changing and the attenuation is getting higher. But it is not that strongly dependent as it is, for example, for GPR. Ground penetrating radars, they cannot inspect if it is just a fresh, because the humidity kills the electromagnetic wave. For ultrasonic, there is not a big issue. We can directly apply it.
Okay, so prediction is how many days?
I mean, we can directly do it immediately.
Okay, immediately. Okay.
Yeah.
Saya bisa segera dites ya setelah.
No, the problem is a little bit. I mean, even more. After several days, it might be a little bit more difficult.
Okay. There is a question from BPE PMO. What is the maximum thickness substrate or material which can be penetrated by UVB? Can the
yes.
tool detect the void inside the concrete?
Look, let's distinguish between reinforced concrete and non-reinforced. If it is non-reinforced concrete, ideal situation, we have only, let's say, the pure concrete, and the only thing which affects the penetration depth is, I mean, how big are the aggregates? The fine concrete, fine aggregates, you can penetrate really much. For the, let's say, mirror 81040 mirror, I mean the old one, yes, we put up to 2.5 meters. If it is a smaller aperture, like for example mirror light, I think we write like 1.2 or 1.5 meters. But even in this situation, no reinforcement. Yes, we can, if we have a coarse grain concrete, coarse aggregates. Yes, the attenuation will grow, will be high, and then our penetration depth is getting limited. So it depends always on the material. Again, we can increase the penetration depth if we reduce the frequency. Then we can penetrate deeper. So for that reason, I mean, average value reinforced concrete, for example, I would say if it is not too coarse grain, yes, up to 2 meters. Again, I have mentioned our customer BAM, federal agency in Berlin, who is using this LAUS system. Many elements are applied to inspect those nuclear waste reactors. With this system, you can penetrate up to 10 meters. But it is always an issue how big your aperture is. If you have more elements in the aperture, you can penetrate deeper because you generate more sound. And all this, what I have said now, it was about non-reinforced concrete. Now, if we're talking about reinforced concrete, where we have rebars, of course, rebars are shielding the penetration. If we have only one layer and the rebars are far away from each other, it is not that bad. If we have second layer, then less energy will penetrate. If we have a third layer, less energy will penetrate, and so on. And then again, it depends on the structure. How many rebars, how close to each other do we have? The more rebars, the less penetration depth. But I cannot tell you, I mean, in advance without to know what are the structural components inside. And then these two belongs together. Then we can have coarse grain concrete with a lot of rebars. And in some cases, if it is really too much steel inside, too much metal, and it is a coarse grain at the same time, we cannot penetrate at all.
Okay. Mr. Hendrikus Pristius saying about talking about UPV measuring strength of concrete. I didn't find any new technology since we have to measuring distance. Uh, uh, I mean, I don't know what is he say. Okay. Maybe I talk to from BPE PMO. What is the maximum thickness substrate material which can be penetrated by UPV?
What is subtract material?
What maximum thickness?
No, which material?
Concrete, yeah.
But I have just replied this question, no?
Already, yeah. Okay, sorry.
Just now.
Okay, many question. In maybe you can choose what you would like to answer. A question and answer. There is a question, but this is Mr. Fahrizan Nur. Apakah bisa mendeteksi panjang tiang panjang? Nah, ini beda nih Pak jawabannya. Nanti kemarin kita udah bahas ini tentang pile test ya. Kalau Bapak ingin tahu panjang tiang panjang, ini pakai memang ada gua sama ultrasonic juga, tapi berbeda equipmentnya ini. Nanti saya bisa share ke Bapak di sesi lain ya Pak ya, Pak Fariza. Is there from Pak Suharwanto, is there an equipment for concrete damage detection underground position, such as foot plate foundation crack lack of homogeneity or other defect from Mr. Suharwanto?
No, I need I mean, you know, at least sketch what does he mean? Because I mean, if it is structurally complex, I
I
mean,
I think this is about is it possible maybe because if we can assess the surface of the concrete, so we can attach the a A1040 Mira 3D so
yes,
to the
yes, this is
surface ya.
possible.
Ya.
This is possible.
Ya Pak Suwaranto ini bisa jadi instrumen yang A1040 Mira 3D itu memang dia mencitrakan dalam beton sampai kedalaman 3 meter. Yang dicitrakan itu defect dalam beton, termasuk tadi Bapak tanyakan ini ya, misalnya defect void atau honeycomb dan lain-lain gitu. Ya jawabannya bisa ya Pak. Oke. Apakah bisa diketahui dikonversi ke kuat tekan beton? Ya bisa Pak. Maybe Andre, you can share about how to convert the compressive strength using UPV.
Okay, this is, you know, this is the most applied technique worldwide. I cannot say much new about that. There are even international codes and standards about how to apply it. I mean, I can refer or even share this code, but the principle is very basic and very simple.
Okay.
Let's imagine you have a concrete, let's say, block. Let's make it very simple. It is just a cube, and you have cubes with a different compressor strengths. If you measure the sound velocity, I mean, it is even done. I mean, many times, yeah, by many researchers, and later it came to the code and standard. They have produced cubes with a different compressor strengths of the same size, and then they have measured the sound velocity in these cubes, and then for each compressive strength value in megapascal, they have measured the sound velocity value in the meters per second. And then if you create a calibration curve, that means for each value in megapascal, there is a value in the meters per second. Then you can later, by measuring, let's say, the sound velocity value, you can find direct value in the megapascal according to this calibration curve. So that then if you have this calibration curve, you can directly go to this on site, measure the sound velocity value, and get the value in megapascal because you have calibrated. So this is how it works. That means normally what you do, you fix some distance, let's say 200 millimeters, 300 millimeters. You put 2 points on the surface. You put your instrument on these 2 points, and with this base, let's say 200 millimeters, you measure the time, and then you obtain the sound velocity value. And this sound velocity value corresponds to a certain megapascal value, the compressive strength value. That's it.
Okay, thank you, Andre. Next question. There's a question about what is the differentiation between ultrasonic and georadar?
Okay, first of all, obviously physical principle in the georadar, electromagnetic waves penetrate the material and used to visualize the inner structure. In ultrasonic, these are ultrasonic waves. Ultrasonic waves are mechanical waves. Electromagnetic waves are, electromagnetic waves. But it is not the point. The thing is, ultrasonic waves can penetrate a little bit better in the material. And for example, if you have humidity or if you have rebars, too many rebars, electromagnetic waves cannot penetrate because they are shielded. They are attenuated too much by this material. So, and for that reason, UT can penetrate deeper. And but for example, UT has another disadvantage. If your rebars, or let's say your defects, are too close to the surface, we have so-called dead zone, a few 10 millimeters, like maybe 20 millimeters, 15, 20 millimeters, where ultrasonic testing is blind. But georadar is a little bit more sensitive on the surface. So each instrument has advantages and disadvantages. I would say better you combine those two techniques for different. For example, what GPR cannot be good about it is, for example, delaminations. They cannot find delaminations well. Ultrasonic testing, vice versa. It is the strongest reflection which you get from them. Yes. At the same time, for example, finding rebars, at least in the first layer, is better with the GPR, because metallic elements are reflecting electromagnetic waves very strong. Ultrasonic waves are reflected not that good, but still, I mean, depends on the application a little bit. Each technique has good sides and bad sides.
Okay, the question is from Mr. Herdiana. Uh, what parameter that explain the different color of graphs showing level of damage in your
Um,
presentation of Mira 3D? There is a lot of picture, a lot of colors, right? Is it it is represented about the level of damage or something like size of the damage or crack inside the.
no. I mean, if we talk about the imaging, we are not about, let's say, let me find some. For example, here, yes. Let's look to this image, for example. Can you still see my screen? No.
Yes, I can see.
You can see. For example, all the elements which are in red, these are just rebars, or this is maybe tandem duct. This one is a big one, or some pipe inside. So the color doesn't say much. The color says it is no longer concrete. For example, here you have a red color. This is a back wall, and then you have 1, 2, 3, 4, 5, 6 rebars, and then you have this, let's say, pipe inside. So the color doesn't say much. The color say it is not concrete. It is something else. So we are looking to the image and interpret it this way. The color, it means it is some foreign body inside. It might be a defect. It might be a rebar. But color is not saying you much anything about I don't know.
It is not it is not a really maybe it's a rebar or maybe it is void. We have
Yeah,
to sure, yeah, we have to analyze it.
you have
Correct.
to analyze it, and then you can only good analyze it in the 3D, because, for example, a rebar has a very clear shape. It is just a straight line inside the volume. If it is a void like honeycomb, yes, it is has a totally different shape.
Okay,
So
thank
we are
you.
talking about the shape of the indication,
Okay,
not about the color.
yes. Yes, there's a question also from KPC. He asked about Ain Bahasa ya, untuk mencek pol listrik mutu beton apakah terdeteksi, berapa milimeter crack dalam struktur bisa terdeteksi. Uh, ini saya bisa jawab mungkin ya, kalau bahasa Indonesia ini boleh. Mutu beton akan terdeteksi Pak, berapa milimeter crack. Nah, maksudnya ini ukuran, kalau kedalaman berapa milimeter sampai dia bisa cek sampai 1 meter 30 cm bisa. Kalau untuk besarnya saya tanyakan ya sama Andre. Andre,
Yep.
how is the minimum size of crack we can detect with our instrument with 3D?
Look, again, it depends a little bit on let's say on the material, but Recently, we have created a reference blocks. These were not cracks, just notches, yes, inside. And the smallest we could really measure, because we don't detect, yes. If we talk about the open cracks, these are cracks which are visible from the surface. We only don't know what is the depth of the crack. And then if we try to estimate the depth of the crack, the smallest we could measure, really, let's say, we have made notches of different depth, like 100 millimeters, 50 millimeters, 20 millimeters. And I think the smallest we could distinguish, yes, it was like, I think 20 millimeters. That was the smallest. I mean, 20 millimeter depth.
20 millimeter depth.
Yeah.
How about the size of geometry? Maybe
No,
in
we could
centimeter, in 1 centimeter, maybe can be detect. Maybe
no,
half.
but if it is open crack, it
Yes, open
is
crack.
just getting inside. Yes, and we catch up only the crack tip. We don't
Okay.
see the wall
Okay.
of the crack.
I mean, if any crack inside, maybe not ink. It is not crack actually. Void, yeah.
Okay, then again, it depends. For example, I mean, what void we're talking? If it is just let's say inclusion, I mean, just a air bubble,
Inclusion, yes. Yeah, bubble.
air bubble. Okay, then as I have told, if it is just a perfect air bubble, I mean, nothing is perfect in the world, but let's imagine this is just ideal reflector. We can say that the such a spherical reflector, which we can, let's say, sure detect, it is like something like 20 millimeters
20 millimeter. Okay.
in
So,
diameter. Yeah.
okay. Jadi ukuran bubble atau defect dalam beton ya Pak yang bisa kita deteksi 20 mm paling kecil. Kalau kalau dalamnya 1,5 meter, 1,5 meter bisa kita detek Pak. Okay, next question. Yes, we have a lot of question here. Okay, whether possible to implement this method to check concrete that is underwater. Yeah.
Look, we get these inquiries quite frequently.
Yeah.
The thing is following. The main advantage of the mirror system is we don't need any coolant liquid, you know, because I mean, but the perfect coolant liquid is a water. So
Yeah.
that means if we would especially create a system for underwater inspection, I would rather go for regular piezoelectric transducers, not for these dry point contact transducers. But the development of such a system is a very, very long way. So that I would rather think if we talk about, let's say, customization of the current mirror underwater, this would be a shorter way. But really, to make it waterproof, it is also a big project. So until now, we didn't have a critical mass on inquiries. These are just very sporadic inquiries, like, can we buy and apply your instrument now underwater? We say no. It would take, I don't know, some 1 year to make such a system. And then the people just disappear because nobody wants to wait for so long, because it is a huge investment, yes, to make an underwater machine um, like that. But I can imagine that it would be possible. We can make let's say an instrument which is waterproof. We can have a cable which gets out of water, maybe even, because how you want to look to the to the tablet PC, or maybe we can take some waterproof tablet PC. But anyway, underwater you cannot see much because the water is maybe not that clean. So maybe the easiest just to have a cable out to outside, and then to have a PC not underwater to look inside, and they collect the data by some robot, maybe, or maybe by the human or whoever. I mean, it might be possible, of course, but it is a long way. It is not something which we can just directly show.
Ya, oke. Thank you, Andre. Banyak yang bertanya memang apakah bisa mengestimasi mutu beton? Ya, bisa jawabannya ya. Jadi semua instrumen yang dipresentasikan tadi sama Andre itu tujuannya adalah untuk estimasi mutu beton. UPV itu mengestimasi mutu beton dan kita bisa juga tahu nilai velocity di material itu dalam artian nanti homogenitas beton dan dalamnya retak. Itu gunanya kira-kira. Kalau yang 3D tomografi ini memang mencitrakan yang di dalam beton. Cuma memang banyak hal yang dia tadi jelaskan, ada keterbatasan-keterbatasan di ultrasonic ini, terutama di permukaan beton. Dia ada blind area sekitar 20 mm, di dalamnya baru bagus gitu. Dan kedalaman penetrasinya udah sampai 3 meter dari tipe Mira 3D itu. Oke. Untuk UPV sendiri bisa sampai 1,5 meter kira-kira penetrasi untuk analisa mutu betonnya. Jadi memang penetrasi itu berhubungan dengan lebih bagus kalau dia metode direct ya, direct dari satu di utara, probe-nya satu lagi di selatan, transmitter dan receiver-nya. Oke. Andre, I see a lot of question, but our time is already I think. What do you think? Still continue?
No, my proposal would be. I mean, it is very nice actually that there is the audience is interested on the technology.
Yeah.
Maybe you can just collect those questions from the people. I mean, they can submit it to you, and you can a little bit let's say sort it, and then either we will repeat it again. I mean, we'll have like uh, asking and answering session.
Okay. Maybe
Separately, you know, but before you just collect a little bit the questions and the people who have questions,
Yeah, yeah.
you know, and we will make just another meeting for that.
Okay, okay, okay,
I mean,
Andre.
any time we will can plan it in. We can have a discussion. Maybe people can put questions directly to me. I mean, also in such a session.
Okay, maybe possible also to demonstrate it. Maybe on the other session, maybe.
Now it is a little bit difficult because all our concrete blocks are underground in our last stock.
Okay.
And the demonstration is a little bit difficult, let's say, because we have to install the camera there and so on and so on. It is, I mean, we can consider it, but then it will take longer time to prepare.
Okay. Oke, banyak pertanyaan ya, misalnya Pak Kiuntoro ya, he has a thick column. Ya Pak, kalau punya kolom yang tebal gitu, kalau bisa direct ya usahakan direct Pak. Kalau nggak ya semi direct ya, ya indirect adalah pilihan terakhir kalau untuk UPV. Andre, thank you for your time. Maybe I think I will do that. What you were saying, I will collect everything and we can organize another session, or maybe you can write the answer by writing. I will send to each
Also
of them.
possible, sure.
Oke, oke. Pak, terima kasih waktu Bapak semuanya. Andre, thank you for your presentation.
You're welcome.
Yeah, some of attendants are asking for how about the metal testing? Maybe we can have that also in 3 weeks.
Sure, we have another conference on the metal testing for sure.
Ya, kita akan share lagi nanti. Oke, dari saya itu aja. Terima kasih, Andre. Maybe you have a close statement, maybe.
Pardon?
Maybe you can close the session.
Yes, sure. Okay, thank you very much for your attention. Okay, some 230 people. Very nice. I appreciate your participation on this session, and I hope we will continue. I mean, if we have such a good interest to the technology and to the ultrasonic testing of concrete, we can just repeat our meetings maybe even on the regular basis, and I'm really happy to provide more information, more knowledge to you regarding this topic. So you're very welcome. You can also, I mean, I appreciate also Zulfikri so for organizing this session. And yes, this is our partner in Indonesia. So please contact him directly. We will keep in touch. Thank you.
Oke, terima kasih semuanya. Materi kan saya bagi nanti juga sesi Zoom-nya akan saya share di YouTube PT Testindo. Terima kasih waktunya. Moga-moga semuanya sehat dan ada yang bisa diambil di waktu yang singkat ini dan kita bisa ketemu lagi di masa yang akan datang dalam keadaan sehat walafiat, berakhir dengan baik dari pandemi ini. Dan semoga proyek bapak-bapak, ibu-ibu semua lancar. Testindo siap mensupport jika terkait produk dan juga nanti terkait pengujian ya. Silakan kontak di WA, WhatsApp, kita bisa diskusikan nanti di luar sesi ini. Dari saya itu aja. Thank you everyone. We would like to end our webinar session. And for Andre, we appreciate everything from you. And people here is very pleased to have your presentation.
Thank you very much.
Okay.
So see you guys.
See you again. Bye bye.
Bye bye.
Assalamualaikum warahmatullahi wabarakatuh.